Hello everyone, in this video we'll be looking at section 13.4, which is differentials. So subsection 1, increments and differentials. In this section, the concept of increments and differentials are generalized to functions of two or more variables. Recall that for a function of one variable, like y equals f of x, the differential of y is defined as dy, which equals to the derivative of, or f prime of x times dx. Similar terminology is used for functions of two variables, that is, delta x and delta y are the increments of x and y. All right, so I'm going to go ahead and highlight that. Delta x and delta y are the increments of delta y, and the increment of z is given by this formula here, which is delta z is equal to f of x plus delta x, y plus delta y minus f of xy. Okay, so now that we know what increments are, let's talk about what differentials are and the total differential. So if z equals to f of xy and delta x and delta y are increments of x and y, then the differentials of the independent variables are dx equals to delta x, whoops, that's just supposed to say dx is equal to delta x, not delta dx, and dy is equal to delta y. And the total differential of the dependent variable d is given by this formula here. Okay, so this definition can be extended to a function of three or more variables the same way, except if I were going to do three or more variables, when I would go to do maybe like x, y, and z, my last variable would be the derivative of the function with respect to the partial derivative of the function with respect to the variable z. So in other words, it would be like f of z, x, y, z, and then d, z, right? Okay, so we've got two things to keep track of. We've got what differentials are. In this case, our dependent variables are exactly, our differentials are equal to dy and dx. And in the case of our dependent variable, this is our increment, and this right here is our differential, our total differential. So the first example here, find the total differential for z is equal to 2x sine of y minus 3x squared y squared. So in order to find the total differential, I need to find first the partial derivative with respect to x, the partial derivative with respect to y, and then multiply it by dx and dy. So let's practice using our different notations. So let's look at the partial derivative of z with respect to the variable x. So remember, we treat y as a constant. So if I did that here in this first term, sine of y is all a constant, right? So this ends up being 2 sine of y, and then minus 6x y squared. And then if I were going to do the partial derivative of z with respect to y, now my x's are constant, so I'd end up with this 2x is the constant and sine of y is the function that I'm looking at here. So the antiderivative, or the derivative of sine, is cosine here, so I get 2x cosine of y minus 6x squared y. And then now if I were doing my differential is dz, and it looks like the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. And we found those, so this one is 2 sine of y minus 6xy squared dx plus 2x cosine of y minus 6x squared y dy. So that is what my differential d of x is. Okay, so now let's look at another one. Let's look at this one. This one's a function of three variables. We need to find all three, right? So let's find our function this time is called w, right? So we need to find the partial with respect to every variable. So the partial with respect to x is just going to be 2x because the y squared and the z squared are constant. the partial with respect to y is just going to be 2y, and the partial with respect to z is just going to be 2z. So if I want to find dw, which is my differential in this case, because my function is called w, it would be the partial with respect to x dx plus the partial with respect to y dy plus the partial with respect to z dz. So in this case, I would get 2x dx plus 2y dy plus 2z dz, and that is my differential dw. Okay, so now let's talk about differentiability. So recall that for a differentiable function given by y equals f of x, you can use the differential dy is equal to f prime of x dx as an approximation for small delta x of the value of delta y is equal to f of x plus delta x minus f of x. So when a similar approximation is possible for a function of two variables, the function is said to be differentiable, right? And our formulas are going to look somewhat similar, right? So here, definition of differentiability, a function f given by z is equal to f of xy is differentiable at this point, this specific point, if delta z, which delta z, remember, is my not my differential, but delta z is my increment of z, right? So if delta z can be written in the form the partial derivative of x at that point times delta x plus the partial derivative at y at that point times delta y plus some epsilon 1 delta x plus some epsilon 2 delta y, where both epsilon 1 and epsilon 2 approach 0 as delta x delta y approaches 0, 0, right? So the idea here is that we figure out what delta z is, and if it can be rewritten in this form so that it looks like this, where this happens, then we say it's differentiable at that point, right? So that's how we're going to answer example 3 here. And the function is differentiable in a region if it's differentiable at each point in our region R, right? Same idea as extending the idea of if it's differentiable at a point and then differential at an interval. Right now we're going to be, or differential at a certain x value and then an interval. Now we're going to be a point and then a disk or a region. So as always, this can be extended to functions of 3 variables, just as it is. We extended it from 1 variable to 2 variables. We can extend it from 2 to 3. We just have a z, a partial with z, and we'd have an epsilon 3 and a z. We'll just look at the case of 2 variables. Okay, so we want to show that the function f of xy is differentiable at every point in the plane. Okay, so what we're going to do is we're going to let z equal to my f of xy value, right, which in this case is x squared plus 3y. And if we do that, then the increment of z at any point, right, because the whole goal of this problem is it says we want at every single point. So instead of plugging in this specific x naught, y naught, I'm going to plug in a generic x and y. And if it's true for generic x and y, then it's true for everybody, right? So here I'm going to put, again, when I go to plug in, when I go to find this guy in here, and when I go to plug in x and y values into there, I'm just going to use x and y for a generic x and y value instead of x naught, y naught. Okay, so then the increment of z at an arbitrary point xy in the plane is, so again, we're plugging in x, y instead of x naught, y naught. Well, remember, what is delta z? That increment of z, that's this first formula that I looked at. It looks like f of x plus delta x, y plus delta y. So f of x, because x is the value that we're plugging in, so x plus delta x, y plus delta y, and then we subtract f of x, y, right? That's that formula there. Okay, so this is what a generic increment of z is. So now we're going to use our function, right? So our function is x squared plus 3y, but now I'm plugging in this for my x and this for my y. Oops, this should have been a y. So I'll go and say x squared, but x is x plus delta x squared plus 3y, but y is y plus delta y. And then minus f of x, so minus my function, but I need to make sure to write minus parenthesis so that I remember to distribute my negative sign. So if I square this, I get x squared plus 2x delta x plus delta x squared plus 3y plus 3 delta y minus x squared minus 3y. Okay, so remember what I'm trying to do. I'm trying to figure out a way, if I'm showing that this is differentiable, I want to rewrite delta x and make it look like this for some functions, the partial derivative of x, the partial derivative of y, and for some epsilon. So one thing I actually should probably do here is figure out what delta x and figure out what my partial derivatives are. So f of x, let's figure out what my partial derivative is, so that way I know what goes here and what goes here. All right, so my partial derivative of this guy with respect to x is 2x, and my partial derivative with respect to y is 3. Okay, so let's color those maybe different colors here. So in this case, let's call my delta x, my partial derivative with respect to x at 2x, and my partial derivative with respect to y, let's call that, we'll go green, and that'll be right here. Okay, so first let's see what cancels out. So x squared cancels out with x squared, plus 3y cancels out with plus 3y, and then I see 2x. What is 2x? 2x is my partial derivative with respect to x, right? So let's rewrite this as 2x delta x plus, and then now 3 is my partial derivative with respect to y. It's going to write plus 3 delta y plus, and now what I have left will be these other kind of remaining pieces, right? So whatever's with delta x that's left is going to be my epsilon 1. So I'm going to rewrite this as delta x times delta x, since I know that I need something multiplied times delta x is going to be my epsilon 1. And then I have no delta y, because I already took care of this delta y, right? So I'm just going to write plus 0 delta y. So now, if I think about all these pieces, there's epsilon 1, here's epsilon 2. I rewrote my delta x, I rewrote my delta x as my partial derivative. This is my partial derivative with respect to x, right? Times delta x plus my partial derivative with respect to y times delta y plus something times delta x. In this case, it was delta x times delta x. So that's my epsilon 1. And then plus something else times delta y. In this case, we kind of had to do a little trick, but it would be 0, right? So in this case, again, this is my epsilon 1, and this is my epsilon 2, right? So this is in the form that we talked about, that it should be x And again, I'm not plugging in x naught, y naught because I didn't want to go for a specific point. I wanted every point, so that's why it looks like xy. So 2x really was my partial derivative times delta x, plus 3 really was my partial derivative with respect to y times delta y, plus I'm just going to put epsilon 1 times delta x plus epsilon 2 times delta y. All right, so I got everything the way I wanted it to. And so since it's in the form that I want it to, that means it is differentiable. Right? And so we'll write our final statement once I get all this written out. So what was the last thing we had to talk about? We had to talk about the fact that epsilon 1 and epsilon 2 both had to go to 0. So let's make sure we talk about that right here as well. So since what is epsilon 1? Epsilon 1 is equal to delta x goes to 0 because delta x is going to 0 by definition there. It says as it goes to 0. So because epsilon 1, which is equal to delta x, goes to 0, and epsilon 2, which is just equal to 0, obviously goes to 0, as delta x and delta y go to the point 0, 0, because that is true, and because it's written in the form that we want, so and we'll just say that delta z looks like f of x, y, z, delta x plus fy, xy, delta y plus epsilon 1 delta x plus epsilon 2 delta y. And again, this was for any xy. It follows that f of xy is differentiable, not just at the point x naught, y naught, but since we figured this out for every x and y, it's for every point. So it's differentiable for, or we'll just say at, every point x, y in the plane, which is exactly what we wanted to show. Okay, so one thing to be sure of here, be sure that you see that the term differentiable is used differently for functions of 2 variables than for functions of 1 variable. So the one we're most used to, right, functions of 1 variable, a function of 1 variable is differentiable at a point when its derivative exists there. Right? If I asked you if a function was differentiable at some point, what you would do is find the derivative, try to plug in that point, and you'd see, oh, it exists, so yes it is, or nope, it doesn't exist, like I have something over 0 and it doesn't exist, so the derivative does not exist there. Right? But that's not how it works in the case of functions of more than 2 variables. For a function of 2 variables, the existence of a partial derivative f sub x or a partial derivative f of f sub y does not guarantee that the function is differentiable. Right? So in other words, just because the partial derivatives exist doesn't mean that the full derivative does exist. Right? Or in other words, and I shouldn't say doesn't mean that the full derivative does not exist, because that doesn't make sense. But just because your partial derivatives exist, because that's how we take the derivatives of functions of 2 variables, we only can do it with partial derivatives. But just because the partial derivatives do not exist does not mean that just because the partial derivatives do exist does not necessarily mean that it's differentiable. Right? So again, just let me repeat that. In a function of 1 variable, if the derivative exists at that point, then it's differentiable at that point. Cool. In the case of 2 variables, our interpretation of the derivative is the partial derivatives of our function x and y, so the partial derivative with respect to x and the partial derivative with respect to y, just because those exist doesn't mean that it's differentiable at a point. Right? Okay, so theorem 13.4 does tell us what is that strong condition that tells us if a function is differentiable at a point, right? So this is why it's called the sufficient condition for differentiability. if a function of x and y, if f is a function of x and y, where the partial derivatives with respect to x and y are continuous, then f is differentiable. So in other words, just because they exist at a point does not mean it's differentiable. However, if they exist and they're continuous, then it's differentiable, right? So the idea is if those guys are continuous, then that is sufficient for you to determine whether it's differentiable at that point. So hopefully you're able to see the difference now. All right, in the next video, we'll look at subsection 3, approximation by differentials.